Hello, welcome to this webinar. I hope everyone can hear me. My name is Iqbal Singh Josan, and I'm going to present this webinar on antenna engineering, part 1 of 2 today. You can interact with me by typing a text message in the chat box, which is on the left-hand side of your screen at the bottom. And if you have any questions, you can ask me by typing in there. And so now we begin. So thank you everyone who is joined this webinar. Okay, so let's get started. So in this webinar, we'll go through some of the basics of antennas. This is meant for people who are new to antennas or even for those who are already working in this area to refresh their knowledge and to just look at what all is going on in this field. So we'll cover the basics of antennas. We'll look at various antenna design parameters which must be considered when we are designing a antenna system. Typically, we must look into input impedance, and then we have size, weight, and power considerations for any antenna system that needs to be designed for wireless communications. We'll look at the field and power patterns. We understand what is beam width, directivity, gain, and aperture, and how it applies to practical antennas. Then we'll also consider the polarization schemes which are used in various antenna systems. And then moving forward, we'll consider the different antenna types that we see in our wireless systems. And moving to some advanced topics on phased arrays, how are phased arrays used, which are basically arrays of antennas, and how they can be used to form beams which can be steered in any direction you want. And finally, what are the applications, some of the uh, applications they find in the smart antenna field and other areas. Okay, so let's begin with the basics. What is an antenna? Now, very simple definition that it's a device which we use to propagate RF or electromagnetic waves or radio frequencies, the signals from a transmitter to a receiver. There must be a transmitter on one side and a receiver on the other side and a radio channel in between. So this is a very common definition understood by everyone, even the laymen know this. Yeah, I have a handset and it has an antenna which I use to transmit signals to the cell tower and so on. Okay, so now this is a picture which shows a real antenna. On a cell tower, you have dish-like antennas which are used for point-to-point transmission. Now let's go to a little advanced definition. When we talk of engineering an antenna system, we look at it also as a transducer that converts a guided electromagnetic wave into a propagating EM wave in free space or vice versa. So a guided wave from a waveguide or a transmission line or a coaxial cable. You see the pictures of those in the slide here. So it converts the guided waves into radiation in free space and vice versa. That means we can use it to do the reverse operation too. When we use it as a receive antenna, we convert a received electromagnetic wave into a guided wave, which ultimately goes to a receiver circuit. So you see the structure of a coaxial antenna cable here on the slide and different shapes and size of antennas. They come in the familiar cell tower where you have these vertical rods on the top of the tower. You have a mesh-like antenna. You have a dish-like antenna used for satellite reception, or you have a waveguide, a horn type of antenna. So they really come in very diverse shapes and sizes. Well, moving a little further, we must understand the antennas are reciprocal devices. What we mean by reciprocal is that they can be used to transmit signals as well as receive signals. So the same parameters apply in both directions. If we say a specific antenna has a typical input impedance of, let's say, 75 ohms, this is true for both transmit and receive. So they are basically reciprocal devices. Now, since they are reciprocal devices, we must use some device to separate the transmit and receive signals because both signals carried on the same antenna. So typically a very, very common device called duplexer is used on the antenna side, which separates the transmit and receive signals going to the electronics. So on the picture you see a typical antenna, the duplexer circuit, which uses a quarter wave lambda by 4 circuit isolator basically to isolate between transmit and receive side. Okay. let's move to the next properties of antennas. Now, as an engineer, I would like to look at as an impedance transformer. Now, what is impedance? Impedance is typically the ratio of the voltage to current at a specific point on the antenna. So a typical RF equipment or a system that you come across in the industry, it will have a typical impedance of 50 ohms. Whereas the free space impedance, if you read any classic text on electromagnetic fields, it's the typical free space impedance is 377 ohms. So antennas come in between. They transform the impedance from an RF equipment, which is 50 ohms, into 377 ohms, which is the impedance of free space. So we can also consider them as impedance transformers. Well, yet another perspective is of an antenna is a band pass filter. Now we know the filters. What are filters? Frequency filters. The filters allow us only a specific range of frequencies to pass through them. So if you look at the specifications of any commercial antenna, you just read through it and it will describe a frequency range. Let's say for a Wi-Fi antenna, your frequency range is written as 2.3 to 2.5 gigahertz. So what that means that it will only receive or transmit frequencies within this range. So it is a band pass filter because it allows to pass only frequencies within this range. So you could represent an antenna as a band pass filter too. If you just convert into a band pass filter in the way we describe circuits, you could describe antenna as a combination of lumped elements consisting of inductors and capacitors, L and C. So as you see on the band pass filter circuit here and the frequency response diagram on the right side of it. So it really also is a band pass filter. Okay. So now let's move on to the fields around an antenna. What all fields we look around an antenna. So any antenna system or any antenna typically, it will have three different regions. The closest to the antenna is the reactive near field. So this reactive near field is something similar to the things you see in a transformer, in a power transformer, where if you place an element within this field, it will have induced electromagnetic current. Now it is not propagating in free space by just staying close to the antenna. And for a typical wire antenna, this field is about typical half wavelength wide. So any half wavelength around the center of antenna is the reactive near field. It's reactive. It could be either inductive or capacitive near field, just like you see in any power transformer. Now beyond this reactive near field, you have what is called a Fresnel field or a radiating near field. And that is given by a mathematical expression, which you see on the slide. It's 2L square divided by lambda. L is the largest dimension of antenna. Like if you have a half wave dipole, which is, let's say, half wavelength long, so you put in the dimension over there. And lambda is the wavelength, the frequency at which, the center frequency at which you are transmitting the signal. So beyond the radiating near field, we have the radiating far field or the Fraunhofer field. Now this radiating far field is of interest to us when we are talking about the long-range wireless communication. Because in the radiating far field, your electromagnetic wave, which consists of two components, electrical and magnetic fields, they are transverse to each other. They are perpendicular to each other. And there is no radial dimension there. It's just a plain EM wave traveling in the direction of propagation. And that is where we receive all our wireless communication signals. So it's very important to understand this distinction in the three fields around an antenna. It becomes even more important when you are actually doing measurements in the field. Like if you have an antenna measurement probe which measures the strength of an electrical field or a magnetic field around an antenna, you must keep it outside the reactive near field. Because inside, if you keep your measurement equipment inside the reactive near field, there'll be mutual coupling between the antenna probe and the real antenna. So the mutual coupling will distort your field patterns and you won't get a true measurement. So ideally, your antenna measurement should be located in the radiating far field. And that is important as we move forward for the slides. Okay, so before we move further, I have one interactive question for you guys so that just we can recap what we learned so far. So just let's go through this, the question and the answer statements here and figure out which statement is true. You can write your answer number in the text box so that you can communicate with B, like which answer you think is correct. So the first is antennas can be considered as high pass filters. Number two is antennas are impedance transformers. Number three is antennas are reciprocal devices. And number four is duplexes are used to amplify signals from antennas. So just think about a moment. I'll give you a few seconds. And if you get the right answer, very good. There is one answer, number two. We just learned that antennas are impedance transformers. Very good. We get another answer. It's number three. Antennas are reciprocal devices. So that's very good response. Okay, let's move to the next slide. What other antenna parameters we need to consider? So the most important, or often you come across any antenna specification, is the input or feed point impedance. Now, as we said before, that impedance is the ratio of voltage to current at any point on the antenna. Now, when we talk about input or feed point impedance, we are talking about the impedance of the antenna at the point where the cable connects to the antenna or where the signal is fed to the antenna. That is typically called feed point impedance. So in the picture you see a half wave dipole, and at the center of it you have a place for connecting your coaxial cable from the RF equipment. So we measure feed point impedance at that point. Now the feed point impedance of an antenna is a function of, it's not fixed actually, it's varying. It's a function of the physical construction of the antenna, like how does the physical structure look like, that will change the impedance at each point on the antenna. And also the frequency or wavelength at which the antenna is tuned or designed around that frequency. And also the height above ground. You know, the ground plane plays a very important role in antennas. The ground is sort of a conductor basically, and it reflects RF waves. It reflects upwards, sideways, whatever direction. So the height at which you place antenna above the ground affects its input impedance too. Now here is a typical table taken from actual measurements of impedance for two different types of antennas. One is the vertical half wave and the other is horizontal half wave. So if you just go through this table, you see if we take the horizontal half wave antenna closer to ground, and we get zero impedance. So, but the vertical one still has some impedance. It's higher, it's a really higher impedance, 98 ohms. So you see that when we place an antenna above ground, we have to see where we want to place this, at what height we want to place it, so that we get the ideal input impedance that we want. Okay. So next move on to the next parameter. Now, before we do that, because impedance is such an important parameter, it must match with the impedance of coaxial cable and the RF system. Now, typical, as we consider a typical half wave dipole has a 75 ohm balanced input impedance. Balanced because it has a very symmetrical structure. You see there is one half wave above and one half wave below in the vertical. And it's a very, very common type of antenna. Now, a typical RF system where a coaxial cable is coming from some RF electronics, it will have a 50 ohm unbalanced. Why unbalanced? Because coaxial cable is unbalanced. So here we have a mismatch. We have 75 ohms balanced on the antenna side and 50 ohms unbalanced on the RF system side. So what happens if there is a mismatch? Consequences of mismatch. Our antenna gain will reduce. So our ERP, we will discuss this in more detail. What is ERP? This is the effective radiated power. So that will be reduced. Why it is reduced? Because of the mismatch of input impedance to the RF system impedance, we get reflections. Our reflected power is not zero. Our reflected power will be some function of some percentage of the incident power on the antenna. And in fact, there is a term describing this. It's called return loss. Now, return loss typically, mathematically, we take it as a 10 times log of the reflected power to incident power. So let's consider one case where all power is reflected because the impedance mismatch is so much that really no power is going into the antenna. All of this is reflected back to the RF system. In that case, RL will be 0 dB. Now, if there is no power reflected, that is another extreme of the ideal case. Then we get infinite. So RL is infinite. So higher the magnitude of return loss, the better it is. Ideally, we should be infinite, but okay, there will be some loss. So higher the magnitude of return loss is desired. So this is the main consideration while designing any antenna system. We must match the input impedance of an antenna to the impedance from where it's connecting to the RF system through a coaxial cable or a waveguide or whatever other means you use. Coaxial cable is the most common one. Okay, let's move on to the next. So how do we match impedance between the antenna and the RF system? We use a device called balloon or balanced unbalanced. So this is typically few coils found around a ferrite core and the construction is shown on the slide. So this is used to balance the 75 ohms on the half wave dipole to the 50 ohms unbalanced on the RF equipment. Typically, if those of you who own a TV system that connects to an outdoor antenna, you will notice something like a balloon connecting between the TV equipment and the antenna system. So that is the purpose of it. It balances the impedance. It matches the impedance so that maximum power is received from the antenna to the TV receiver. And the same principle also applies to all other types of antennas, whether it is a cell tower antenna or a handset antenna or whatever antenna you are using. Okay. So now let's move on to what other physical considerations are there for design of a real antenna system. So size, weight, and power. Now these are very important considerations for practical antennas. Because at the same frequency, if we want to increase the gain of antenna, let's say we have a cell tower and which covers only 2 miles. And now there are more subscribers coming into our network, and we want to increase its coverage to, let's say, 8 miles. So what it means, we can't change the frequency all the time. Frequency is a spectrum allocated to the carrier. What we mean, we may need a higher or larger antenna or bigger antenna or maybe at a bigger height from the ground. So and if we can't do that, then we have to change frequency. We have to get a frequency spectrum allocated that's higher than the current one. So at the same size, higher frequency yields higher gain. Also, base stations and access points, they are usually don't cover more than a couple of miles typically. Typically, most of the base stations and access points cover even less. Access points are only few hundred feet for Wi-Fi or even less than that. It could be within one small building. So their swap is relatively a minor concern. Minor concern, well, there may be some concern, but it's not a major critical factor over there. Well, now let's go on to the antennas in smartphones, laptops, and tablets. Now there, of course, it's a critical concern because the space is limited in a handheld device, and you have to think about how do I place antenna inside my laptop or inside my smartphone. I need to be able to receive Wi-Fi signals or 4G signals or 3G signals. So there is a big trade-off between design, performance, and placement. We have to figure out how do we place antenna inside the handheld device where the space is already a constraint. Plus, there is so much of other electronics, the hardware inside the handheld device that would absorb the electromagnetic radiation. You won't get full performance from any transmissions from the handheld device. So this is definitely a critical concern there. When designing antenna, you have to consider what is the weight of the antenna, what is the size of the antenna, and what is the power consumed by the antenna, because battery power is limited in a handheld device. Well, here you see a picture where you see the two antennas on the two sides of the ground plane in a handheld device. This is one case. This is one way we can place the antennas. This is basically they are printed on a ground plane, on a printed circuit board and placed at the back panel of the handheld device. This is one way of doing it. And the other way of doing it is you just place them side by side. When you don't want to have two antenna feed points which are far apart from each other on each side, but of course it will sacrifice some performance. You will get only signal, the gain will be maximum only in one direction, on the side direction, not on the other direction. So there is a trade-off there. This is one example of doing a trade-off between design, performance, and placement. Okay. Now moving on to other special applications in the aircraft or satellite. This is a very critical concern. Power is limited. There is no way you can exceed. You have to reduce the consumption of power by any antenna system to the minimum possible. Plus, how do you place antenna? Where do you place antenna on the satellite or on the aircraft? So you see typical locations on an airplane where antennas are placed. But definitely this is a big concern when designing antennas for these devices, for these vehicles, the aircraft and satellite. Okay, now let's move on to a little more detail on the field and power patterns. So any antenna will have typical electrical and magnetic field pattern as shown in the slide. This is a three-dimensional picture you see. So in the direction of propagation, you see there is a main lobe, and then there are minor side lobes. So any antenna field and power pattern will look like this, because the antennas are directional. Most of the antennas are directional. They will have main lobes, minor side lobes, and nulls where the antenna gain is minimum actually. So any field power pattern will look like this. Is a familiar picture. If those of you who are already working in this field, or those who plan to work in this field, you will come across these patterns many times during day-to-day your life. Now, okay, we have a quick question from Veda Prabhu. So that you can have diversity. Yes, you are right. So you can have diversity in antennas. We'll consider this advanced topic, I think, in part two of this webinar series, and there we'll cover this diversity in detail. You can have multiple antennas to cover multiple directions. So in this slide, you see the electrical field and the magnetic field, the H field and the E field, they are transverse to each other, or at 90 degree or perpendicular to each other. Now this is how the electromagnetic field will look like in the far field, when it's a far field from the antenna. We are not near the antenna in this case. We are in the far field, and there's a planar wave propagating in this direction, in the direction of propagation, consisting of E field and H field, which are perpendicular to each other. Okay, let's move to the next one. Now fields are represented in spherical coordinates. This is the most common coordinate system used to represent fields. As you see, the r, theta, and phi. Well, okay, we have another question coming about MIMO, the MIMO antenna. Yeah, we are going to cover this in the second part of this webinar, which is happening next Saturday. So in this webinar, we are only talking about the basics of antennas. So we will definitely cover this MIMO in the next part 2 of 2. Okay, so let's move on to this topic. So we have this azimuth angle, which is in the horizontal plane, and we have the elevation angle in the vertical plane, and the theta, which is again, there's two ways of representing the vertical elevation, theta or alpha. Theta is 90 degree minus alpha, you see. So we represent fields in two planes, horizontal plane and vertical plane. Well, this is the coordinate system we use, but ultimately it's horizontal plane and vertical plane. So whenever you see the characteristics of a real antenna, you will see the beam width represented in two directions, horizontal and vertical, or we also call them E field and H field patterns. Well, there are some mathematical expressions here which are used to represent the normalized E field pattern. Well, I won't go into the mathematics in detail about this, but you can just look at what we do here is that we divide the electrical field strength at a specific point in the field pattern with the maximum field strength, which is in the direction of propagation, and that gives us a normalized pattern of E field. So when we do actual antenna measurements, this is how we do it. We use this formula. We just divide by the maximum E field strength. We measure the electrical field strength at a specific point and divide it by the maximum field strength, and then we get a normalized pattern, a normalized number, which we use ultimately to plot the field pattern that you see in the side lobes and the nulls and the main lobes. Okay, then there are other expressions. There is a normalized azimuth pattern of field. So zenith is the vertical plane pattern, and azimuth is the horizontal plane. And then we have a normalized power pattern too. The Poynting vector, which is the instantaneous power density. Here, this is the expression you use. What is the instantaneous power density at a specific point in the field pattern? Now, since we are considering only the far field region of the antenna, we don't have any radial component. You see, all these expressions have only measurements done with respect to theta and phi. That's it. There is no radial component because we are making all these measurements in the far field of the antenna. Okay, let's move on to the next slide. So these are the units used to measure electrical field and the magnetic field, and the Poynting vector. We have volts per meter for the electrical field and the amperes per meter for the magnetic field, and the watts per square meter of area is the Poynting vector or the instantaneous power density. pictures of some instruments or vector network analyzers which are used uh, to make these measurements in the field. Okay. Now let's pause for a moment and go to this question. So which one is true? Balanced antennas can be directly connected to unbalanced transmission lines. Balloons may be used to amplify the signals received from the antenna. Balloons must be used to connect unbalanced transmission lines to balanced half-wave dipoles. Duplexes may be used to replace balloons. So very good. Some answers are coming in. Number 3. So balloons must be used to connect unbalanced transmission lines to balanced half-wave dipoles. So all of you seem to be getting a hang of it. If you go to the field, somebody asks you, you will say, oh yeah, you need a balloon. You can't operate without a balloon. It will cause reflections, it will cause power loss, it will reduce the efficiency of the antenna. Excellent. Okay, let's move to the next one, the half power beam width. This is again a very important parameter. Whenever you look at the specification of any a base station antenna or even a handset antenna, you will have this figure, HPBW, half power beam width. This is basically, earlier we have seen any field pattern, it looks like this lobes. There's a maximum, a main lobe in the direction of propagation, and then you have side lobes, and then you have a rear lobe also. Beam width is the angle between the directions where received or transmitted power is half the maximum power, minus 3 dB. So along the lobe, you have maximum power point, as you see on the slide. It's represented by 1.0. But if you go down on the lobe, you have 0.5, which is half. There's a point here, which is exactly half of the maximum power. If you measure the angle between these two half power points, you get the angle, that is the beam width. And then often the beam width is specified in 2 directions, vertical and horizontal. Like if an antenna specification says you have 80-degree HPBW in E plane and H plane. So that means in vertical plane it's 80 degree and in horizontal plane it's also 80 degrees. It could be same, it could be different, depends on how the antenna is designed. Okay, so let's look at the next one. What is next in store for us? So now beam width and gain. The lower the beam width, higher the gain. What it means, the narrower the beam, the higher the gain. So for a typical half-wave dipole, I would say the beam width may be 78 degrees. It's very typical, very close to this number in the real antennas too. And same for any other aperture antennas. The beam width will be 78 degrees. But if you look at a parabolic antenna, like the dish antenna used for satellite reception, there it may be just 1 degrees. Now, why we keep the beam width so small here? Because it results in higher gain. The signals from the satellite are so weak that you need a much higher gain to make sense of the signal. So you keep the beam width very low, just 1 degree or 2 degree or even less than that. So lower the beam width, higher the gain. Well, now let's introduce ourselves to the concept of an isotropic radiator. Well, there's another question, what about relation between beam width and SLL? So this I'll revert back to this answer later. I'll email you, or since we have limited time within this webinar, I'll definitely respond to this question later. Okay. Concept of isotropic radiator. So isotropic radiator is a point source of electromagnetic waves at the center of a sphere, and it radiates uniformly in all directions. Now, why this is a theoretical antenna, basically. Practically, nothing like isotropic radiator exists in the real world. But we use it as a conceptual reference for any real-life antennas. So we consider an isotropic radiator as a uniform, as a point source of EM waves at the center of a sphere, and it radiates uniformly in all directions. Now, we'll see how we use the concept of this concept in our real-life antennas. Okay. So now let's look at directivity. This is another very important parameter, since the real antennas, they have some direction in which they transmit or receive. They have a directivity. So this directivity D is the ratio of max power density to average power density over the whole sphere. So this is a mathematical form, but in layman terms, what it means? It means that how directional the antenna is. Now, if you look on the left-hand side, you have the isotropic radiator, which has a directivity of 1 because it uniformly radiates in all directions. It has no preferred direction. In a real-life half-wave dipole antenna, the directivity is measured to be 1.64. So the more this number D, the more directional this antenna is. So typically, all the parabolic antennas or dish antennas will have much higher directivity because they have also a very narrow beam. Okay. Now let's move on to the next one, the gain. Now, how do we define antenna gain? It's defined as a multiplier which is antenna efficiency factor K, which may be between 0 and 1, multiplied with its directivity. Now why we have this? We have directivity, now we have gain. Now in the real systems, you have some losses on transmission losses, the losses on the cable that connects to the antenna, and maybe other losses too. Okay, so we have to account for those. So there is an efficiency. The efficiency of any antenna system will not be 100%. It should be maybe 0.8, 0.7 or something like that if we consider all the losses. So gain is the real parameter which tells us that what percentage of losses are there in the antenna. So units used for gain, they are referenced over isotropic radiator. In decibel, it means dBi, means dB over isotropic. So as we just discussed, that isotropic is just a conceptual antenna, but it's used as a reference to indicate the antenna gain or directivity of real antennas. Well, for an isotropic radiator, typically the gain is 0 dBi, and for a half-wave dipole antenna, it is 2.16 dBi. Now there is another expression that can be used to calculate this gain from the field and power patterns. Now, from practical measurements in the field for the E plane half power bandwidth and the H plane half power beam width, you can use this formula to calculate the gain. So this is the RF engineers will prefer using this formula because this formula gives us a practical measurement of gain for a typical antenna system. Now let's move on to the next one. What we have for us, we have effective aperture. Now this is the electrical capture area of a receiving antenna for incoming electromagnetic waves. Now you know the physical size of antenna will be okay. You will say that this antenna is 2 meters wide or 3 meters wide, but that does not define the real electrical aperture. The electrical area that antenna uses to receive or transmit will be bigger than that, typically be bigger. So mathematically, we define it as a ratio of the output power that we get out of the antenna to the incident power density, which is in watts per meter square. So just make these measurements, and the result you get is some area which gives you the effective aperture area. And it definitely differs from the physical area that you have on the antenna. Okay. So now what is the relationship between effective aperture, directivity, and gain? So more gain requires large effective aperture. This you must have seen the big parabolic dish antennas, they have higher gain. This we have seen earlier also, the more size gives you higher gain. So definitely there is a relationship there. So effective aperture, more effective aperture gives you more gain. And also higher frequency gives you more gain. So this is the expression that can be used to define the relationship that we just discussed. Okay, let's move on to the next one. The effective isotropic radiated power. So this is the product of the antenna gain and the net input power after transmission losses, product of GT and PT. Well, in terms of dBi, you just make an addition. GT in dBi isotropic to an addition of PT, the input transmission, the net input power after transmission losses. So in practical designs, we must consider all the transmission losses involved in the cable that connects to the antenna. Now here there is an example, a numerical example of how do we calculate the EIRP. So if we have a 1 watt or 0 dB transmitter, the transmission losses are minus 3 dB, and the antenna gain is 34 dBi, we get an EIRP of 31. So this is effective isotropic radiated power with respect to the isotropic antenna. Now then we have another term which sometimes people confuse with EIRP. It's called ERP, effective radiated power. So there is a little difference here. Here we don't use the isotropic antenna as the reference. Rather we use a dipole, a real half-wave dipole as the reference. So you see the expression used for gain here is GT with dBd, the decibels with respect to the dipole antenna. So since a dipole antenna has a 2.16 dBi, that comes into the calculation here, as we see in the next slide. So you see here our gain is 31.84 dBd, which is less than the isotropic gain because we are taking reference with a dipole antenna. So it's very important to remember this difference, EIRP and ERP. There's a difference of 2.16 dBi. You can express in either of these terms. Mostly people use EIRP, but yeah, people can use ERP also. Those who are more on the practical implementation of antennas, they will use this term ERP. So it's very important to realize this difference. Well, now let's pause for a moment. Which one is true? ERP is the same as EIRP. Electrical capture area of an antenna is different from its physical area. Antennas are non-reciprocal devices. The gain of a half-wave dipole is 2.16 dBi. Yes, anyone? Okay, very good. Number 4 is correct. Number 2 is correct. So we are getting a hang of it. Very good, excellent. Okay, so moving on to the next one. Now, this is a very interesting topic in antennas, the polarization. Some of you must have heard of this. The antennas are polarized. Now, polarization means how is the electrical field oriented in the far field of antenna. As we have seen, discussed before, that the E and H fields are perpendicular to each other. But the E field can be either vertical or horizontal or at an angle. Okay, so it could be rotating also in left-hand direction or the right-hand direction. So that gives us polarization of the antenna. So there it could be linear polarization, which could be horizontal, vertical, or linear at 45 degrees. It could be circular polarization, which is often used in the satellite transmissions. The antennas used for satellite transmission, they're usually circularly polarized. It could be left hand or right hand circular polarization, or it could be elliptical. The electrical field rotates in an elliptical. It traces an ellipse as it rotates. So it could be again a left hand or a right hand. Okay, so let's look at how this is done. Okay, so in a linear, I think I move for one slide. Let me go back a little. Yeah, so linear vertical polarization. So typically all our telecom, in the telecom we use vertical polarization because you see the cell towers, you must see these rods are in vertical direction, and the handsets that people hold in their hands. There's another question, can we talk of polarization in near field? Well, definitely yes, we can talk, but we cannot talk in more detail at this point. We'll cover in this in a future webinar. Thank you. Okay, so so in the vertical, so all the the base station antennas, the handset antennas, they typically have vertical polarization. And then we could also have horizontal polarization, where you see the antenna used for TV reception or even for some VHF and UHF reception, they typically will have the horizontal polarization. And then we need to understand this cross polarization. When we say a linear vertical, it's a cross polarized, it's a cross pole of linear horizontal. This is a typical term used by the professionals that, okay, linear, this antenna is a cross pole of the other one, which is horizontal. Now the circular polarization, which is right hand means if you look in the direction of propagation, the E field is rotating in the clockwise direction. And if you have a left hand, the electrical field will rotate counterclockwise, like this. Then elliptical, you don't have a perfect circle, but an ellipse. An ellipse is traced by the electrical field. The electrical field rotates in an ellipse in the clockwise. This is the right hand elliptical polarized signal. Now left hand, you will have a counterclockwise. So I'm quickly going through these slides because they are pretty straightforward. And cross polarization, right hand is a cross pole of left hand in both cases, circularly polarized and elliptical polarized. Okay. Now how do we measure polarization? There is a term called axial ratio, which is simply what? A ratio of the major axis to minor axis. And if you see the table, in case of linear polarization, we have only one axis. We call it major axis. So axial ratio is infinite in that case. For circular, we have equal dimensions in both major and minor. then the number is 1. And for elliptical, it will typically more than 1. So axial ratio will be a parameter defined for a polarized antenna. When you have polarized antennas, this is a typical parameter. The value of this will indicate how much polarization is there in the antenna. Well, polarization mismatch. Now this is again very important. Now let's say you have a transmit antenna which is linear polarized horizontal, and you have a LP vertical receive antenna. What will happen? You won't get any signal because the antenna must be oriented in the same direction as the transmit antenna. If it is linearly polarized, if it's horizontal, your receive antenna must be horizontal. Now if this happens, this is called polarization mismatch. So transmit and receive antennas must have same polarization for maximum power transfer and signal strength. Here, if you align both antennas in the same direction, you get the maximum signal. Okay. So what is next for us? Now here you typically see a circularly polarized CP transmit antenna, which has a horizontal component of electrical field and a vertical component. Now here, of course, if your receiving antenna is, let's say it's linear polarized, you can still receive a signal, but you will receive only the vertical signal. Your typically your received power will be half of the full power. So you will get 3 dB less signal power in case of this type of orientation. For full power reception, you must have a CP antenna on the receive side too, so that you can receive both horizontal and vertical signals. In this case, you are receiving only the vertical signals, not the horizontal ones. So your signal power is half. And that we can say we have a polarization mismatch. Well, there is a question, then why use linear? Well, linear because, of course, it's a matter of implementation. Of course, there are benefits for having a polarized antennas, but that will add to the cost of your handset, the cost of your base station. To keep things more practical and commercially deployed, we use linear antennas mostly. But definitely, you definitely have a good point here. We can improve the performance of signal by having a circularly polarized signal, which is, of course, it is used in satellite communications because there definitely the stakes are high. Your signal is so weak, you must have both components received. But in terrestrial communications, you can achieve acceptable performance with a linear polarized signal. It's only a matter of implementation. So yeah, some of you have given the answers for this. Number one, a linear can receive signal from a CP antenna, and the HPBW of an antenna can be calculated from its smeared field pattern. Very good. That is very good. Okay. Now let's quickly go through the antenna types. Different types of antennas that we see around us. You will have a skewer loop. These are wire antennas. A loop, which is you will see on top of some TV equipment. And then you have ferrite loop, which the AM/FM receivers will have a coil wound, and within there's a ferrite core. And then you have a half-wave dipole and a folded dipole. So they come in different shapes and sizes, wire antennas. Well, this is long wire antenna, which has been used for long wave and short wave. Radio amateurs or the hobbyists who use the citizen band, they often use these long wire antennas, twin lead, rhombic, and helical antennas. Well, we are not going through the details of each type of antenna, and that will definitely be a special course in antenna design. But in this webinar, I'm just exposing you to like how antennas look like, how different antennas look like. So these are the antennas used on your routers and switches and on your cars, automobiles. You have telescopic antenna. You have this Yagi-Uda antenna, which is used for TV reception. Well, we have more wire antennas coming here. This is a log periodic dipole array. Now this is a antenna which is a wideband antenna. There's not a single dipole, but an array of dipoles here, ranging in size from small to big. So that means it can cover a range of frequencies. It could be typically 14 to 70 megahertz range, and it gives you a wideband reception. It's used for some special applications, used by radio amateurs too for wideband reception. Not very common with the consumer electronics type of thing, but they are used for specific applications. Well, we have more wire antennas coming. Oh, now these are interesting ones. The rectangular spiral and the spiral. So here you fabricate these antennas on a printed circuit board, where within a small surface area you can achieve much longer lengths of antenna elements. Well, okay, some facts about the wire antennas for lower gain applications, 2 to 3 dBi. Helix antennas have a little more higher gains, 8 to 15. Generally narrow bandwidth, Yagi, Uda, and log periodic have broad bandwidths and so on. Okay. Now we come to aperture antennas. There is a reflector, parabolic dish, and horn antenna, and it's a reflector with multiple feed horns. So all depends on what type of applications you have for these antennas. And then we also have a parabolic reflector, which has a hyperboloidal reflector in the front of the reflector, and then that helps to make the beam a parallel beam out of it, a plane beam actually, that comes out of the reflector. Otherwise, you will have a spherical wave coming out of the antenna. So use this reflector to make it a plane wave. Well, these are another interesting shape, conical log spiral. A flat panel is again very common. This you will often find in wireless LAN applications in enterprise, uh, in some enterprises where you use these flat panels to communicate from one building to another, or even within the building to cover one specific area that needs to be covered by wireless LAN. They use a flat panel. But it's of course, this shape is used in other applications too, even for your normal reception, normal TV reception. Okay, moving on to the next slide. We have, this is a waveguide microwave lens, which is, we use the concept of a lens, an optical lens. So because the EM waves, they work on the same principle as the light waves. So here we use a lens, which is made of a dielectric, like a polyethylene or Teflon, and it helps to converge the beam or diverge the beam or make it a plane beam as we want. So uh, the main benefit of microwave lenses, because the dielectric lens is made of materials like Teflon and microwave, the shape can be adapted to the shape of the structure. So in specific like military or defense applications, it might be very useful, where you have size, weight, and power is of critical concern, because it's lightweight dielectric that is used to make the microwave lens. So it could be very helpful for designing low profile antennas which are hidden in the structure, or which needs to be lighter in weight. Okay, let's move on to the next one. Some facts about aperture antennas. You know, the gain is a little higher, 3 dB to 20 dB isotropic, and used for special applications like satellite, radar, microwave, relays, space communication, or even in astronomy. Maybe you put this type of antenna aboard a communication satellite. Now we come to another interesting antenna type, a fractal antenna. So we use the concept of fractal, which is repetitive geometries which are used to construct an antenna. So here again, you can achieve a much longer length of antenna element within a small space. These are fabricated in on a PCB or some other surface. It can be used. The antenna length is much longer, but physically much smaller. So somebody is thinking, oh yeah, that's Minkowski fractal. Very good. So Veda Prabhu from India, he is a response. Very good. So I want to share with you is typically the Minkowski fractal. This is excellent for multi-band and broadband applications, and these are fabricated on surfaces with small dimensions such as portable devices. Okay. So phased array antennas. Let's come to a little more advanced type of antennas where we have an array of antennas. We don't have one element but multiple antennas. As you see in the picture, you have 1, 2, 3, 4, 5, 6, 7, 8 antennas installed on a panel, and you can use this type of a phased array of antennas. It could be a linear array in one straight line or a flat panel in 2 dimensions. So you know, this type of array arrangement enables us to build a beam, to steer our beam in whatever direction we want. We want to move it in left, right, up, down, we can move in that direction. So this will enable us to scan or do a radio scan of the surrounding area, like a typical radar application, or we use a targeted communication with users. Like let's say we have a group of users in a certain geographical region. Like when you're in the battlefield, the military needs to transmit signal in a specific direction. So they will typically have phased array antennas. Or even in the LTE, MIMO, and other applications, this arrangement is of very good interest, because you can enhance the signal to noise ratio by steering the beam in one specific direction instead of dissipating all your RF energy in all different directions. So it's on demand basis. Like in the morning time, you need beam in one direction. In the evening time, you need in a different direction based on user behavior and where the users are moving. So this is a very interesting configuration for that purpose. Well, as you see, you can steer the beam up or you can steer the beam down. This is one typical demonstration of how we can use phased array antennas. So let's look at it, this phased array in a little more detail. Okay, before we have, this is a typical picture of a 16 element flat panel which can be used for this array arrangement. Well, now, so here you see a typical detailed picture of a phased array. You see a power divider and there are 8 elements, 8 antenna elements, and the separation between any two antenna elements and two adjacent antenna elements is between lambda by 4 and lambda by 2. They need to be, no, why it has to be half wavelength apart? Because of the reactive field. See, if we make it closer than that, then there'll be mutual coupling between the elements and we cannot achieve the desired field pattern. So the spacing between the elements is very important here. Otherwise, we won't be able to achieve the objective of to be able to electrically steer the beam in whatever direction we want. So the spacing between the elements is very important when you're considering phased array antennas. You use a network of phase shifters. There is a phase taper and an amplitude taper between the elements. This is how you achieve it. So you see in the phase taper, you have the same signal is applied to antenna elements with a phase difference. 1 phi, 0 phi, 1 phi, 2 phi, 3 phi, and so on up to 7 phi. Same with the amplitude taper, you have amplitude taper. The amplitude changes from A1, A2, A3, A4, and so on up to A7. So let's see how we make this happen. Okay, now you see, this is how we are looking at how the beam tilts in a phased array. Now you see, the beam tilts in the direction of the maximum phase delay. You know, the antenna element, the rightmost element here has the maximum phase delay. So the wavefront is slow to transmit. And in the first element on the leftmost side, you have no phase delay. It's 0 phi. So naturally, what will happen as the signal, as the RF, the EM waves transmit, you will find a tilt in the beam that is transmitted, and the beam tilts by an angle theta s, which is called the scan angle. So by using this complex network of phase tapering and amplitude tapering, you achieve the steering of the beam. By changing these values, what phase difference you apply the signal to each element, you tilt the beam in the desired direction. If you make it the opposite way, like if you make the rightmost element 0 phi and the leftmost element 7 phi, the beam will tilt in the other direction. And depending on how much taper you have in the phase or amplitude, you will achieve the desired scan angle, theta s. Okay, so we just saw how the beam tilts. Now, there's another situation. If the element spacing between the elements is more than one wavelength. Now, earlier we saw that the spacing should not be less than half wavelength. But what happens if the spacing is more than one wavelength? Then we get a phenomenon called grating. We get grating lobes. If we make it more than half wavelength in a phased array element spacing, we get additional lobes on the sides. You see, there's a main lobe and there are two additional lobes, one on the right side, one on the left side. Now, this is an undesirable situation. We don't want our RF energy to be dissipated on the left and right side. We only want it in the main lobe. So again, there is another, the spacing between the elements should not be more than single wavelength, and it should not be less than half wavelength. So we have just seen how the spacing between elements is such a critical factor. Now, what happens with the field patterns of a phased array antenna? Now, this could be a challenge. Now we have not one antenna, but multiple antennas, and how do the field patterns from each antenna add up? So we define a term called array factor. So array factor is nothing but an antenna pattern for a given amplitude and phase taper, assuming each element is a point source. So we just assume that each element is a point source, just like an isotropic radiator, and then we mathematically calculate, okay, what is the antenna pattern? And this will be used as a reference to achieve our target side lobe performance by adjusting the element spacing, amplitude taper, and the phase taper. Now, how do we build a composite array pattern? So we defined array factor, but how do we really build a composite array pattern? If we have all antenna elements identical, like all are, let's say, half-wave dipole antennas or whatever shape you have, you just multiply the array factor, which is mathematically derived, with antenna pattern of one element. Because it's much easier to derive the antenna pattern of one single element. And if you assume that all elements are identical, we just multiply the array factor with the a antenna element. So what about using quarter wavelength is another question from Matthew. Yeah, of course, you can use quarter wavelength, but that is a limit. Beyond quarter wavelength, you will have more mutual coupling. So typically, we have a range here, a quarter wavelength to half, which is defined, which is tolerable in case of phased array antennas. Okay, for non-identical antenna elements, now it is much more challenging because you can't simply multiply the array factor with the antenna pattern. Here, you actually have to make measurements in the far field region and perform a vector sum of all the measurements created from each element. Okay. Now, multiple independent beam forming. Now, arrays typically can be used to form multiple independent beams which transmit in different directions at the same time. We could use sub-arrays or we could use beam forming networks. There's a list here, a Butler matrix, a Blass and Noye matrices, Woolen-Weber array, a McFarlane 2D matrix, Rotman lens, Bootlist license, and dome lens. Now, we won't go into full detail of all these. Just for your introduction, like you can dig deeper into these areas if any one of these networks is of interest to you. But how do we, let's scratch the surface of it. How do we achieve that? So in sub-arrays, we divide the antenna element array, which is a two-dimensional array, into independent sub-arrays. Now you see in the picture here, we have divided the antenna array into 4 sub-arrays, sub-array 1, 2, 3, and 4. So simply instead of one array, we have 4 arrays, and each of them have their own independent feed and independent beams. This is much simpler to implement, it seems, because you just simply wire it accordingly and achieve different beams. Okay. So other ways you could deploy a beam forming network. Now this is a typical example of a Butler matrix that we saw in the list earlier, and I have given some formulas here which can be used to calculate how many different elements we need. So here the typical this network consists of directional couplers, fixed phase shifters, and then you have antenna elements. And then you have, if you see on the antenna inputs, you have 8 antenna inputs, and each of these antenna inputs ends up in 8 different beams. You see there are 8 different beams originating from the antenna array. So if you have n beams from n elements and n inputs, then n is defined by 2 exponent p, and number of directional couplers is given by this formula you see on the slide, and number of fixed phase shifters. For example, if there are 8 elements as you see on the slide, you need 12 directional couplers and you need 8 fixed phase shifters. Well, now one more interesting application which comes out of the phased arrays, adaptive arrays. Now what are adaptive arrays? They are also called smart antennas. See, the word smart is very common now. Anything new become, obviously it's a smartphone, smart antenna, smart this or smart that. So we also have smart antennas, which are nothing but adaptive arrays. Adaptive arrays have been used in the past in special applications and in defense and military and communication applications, or very specific applications with satellite communications. But you know, they have interesting capabilities. So here what we do, the antenna array, it processes received signals from all sides, from wherever it's receiving it based on this beam pattern, and shapes the beam pattern to achieve desired performance. So it is adaptive. You know, it receives the signals and it calculates using some algorithms and DSPs that, okay, I am getting strong signal from this direction. Let me steer the beam through that direction, and so that I can maximize my signal to noise ratio. Now that has very good applications to reduce pickup from noise sources. And it can even be used to compensate for mechanical or electrical errors in the antennas, failed elements, blockage from nearby structures, or even if we have sources of electromagnetic interference, we could steer the beam away from the source of EMI, as we see in the next slide. So what happens here? What the antenna does? Now let's say in this picture, we have this phased array antenna which needs to communicate with the satellite. The communication target here is the satellite. But it has a nearby high voltage kilovolts power line, which is a source of very noisy source of EMI. Now it can you know, it can overcome the signal received from the satellite, and what you will all get is noise. But to boost your signal to noise ratio, what the antenna does, when it notices there's a source of EMI coming from this side lobe, then it will change its beam pattern. It will create a null in that direction. A null in the direction, that means it will no longer receive the noise signals, or the strength of noise signals will be much reduced compared to the signal received from the satellite. And some of the algorithms which are used to process the incoming signals, they are listed here: the least mean squares, the sample matrix inversion, recursive least squares, conjugate gradient method, and constant modulus algorithm. Now, this is for the experts who are really designing these type of antennas. But really, they are intelligent and smart, because they can change their beam pattern based on which direction they want to receive the signals or transmit the signals. Okay. So now here I have given a list of some research papers and books which you can use to dig deeper into each of these topics. Now, so for everyone's information, I know you have asked many questions, and I have answered some of them. Some of them I may not have answered, but I definitely answer you and send you in email whatever more information I dig out on these topics, and I can share with you. We are learning together in this. Okay. Now, all of you who are attending this webinar, you will receive a copy of the slides from this webinar for your reference. And then there's information to claim a professional development hour and the certificate of completion. So after this webinar ends, you will be directed to another webinar forum page, which the link is given here. You will get this link in the slides that you receive in the email, but even now you will see it on your screen when the meeting ends. And there is a feedback form you need to complete, and there is a problem statement from this webinar, a simple problem statement. You just respond to the statement and you complete the requirements for certificate of completion, which will be emailed to you within 2 business days. And then you have my information here, my email ID. I am open to any emails from you for any technical questions from this webinar or any other services that we provide, which are listed on our website. And you can also Twitter me if you want to. So any specific question you have at this point in time, which I can quickly answer, you can type in the text box. Okay, so it seems nobody has a question at this point of time, but you can definitely email me, and I will try to all the remaining questions which I did not have enough time to answer at this point of time. Okay, thank you, and have a good day or good night wherever you are. I know we have a global audience here from different countries, and it's good to know that there are so many people around the world which are interested in wireless communications, which is a very growing field everywhere in the world. Thanks for your interest in this webinar.